Good afternoon, all. Welcome back to PSM 150X. We have about 4 weeks left, and obviously this week you're writing your class test 2, right? So today we online, tomorrow I'll see you on campus at around 9. And yeah, so I'll obviously do a small debriefing on the test. But like I said, yeah, anyway, we'll talk about that tomorrow. But today we're just gonna end off on topic 8. I did label this topic 9 and I realized I just got to do a small section of topic 8 before we can conclude it. And then by tomorrow we'll start on topic 9, and then yeah. Can I just ask a quick question? We know you guys writing maths? We know you guys writing maths.
Monday, sir.
Monday as in next week Monday.
Monday. Yes.
Oh, okay, thanks, Nelusi. So the East time, I just thought maybe there will be, assessments back to back. Okay, all right. So moving on. Um, Last week we discussed the moment of inertia, and obviously we looked at varying objects. Um, and yes, I talked about that. And what we're going to be doing today is essentially the rotational kinetic energy. And yeah, that's the main objective for today. And then next week, I mean tomorrow, we're going to do fluids, right? It seems like we have another chapter after that. Not a whole topic, but just in individual sections. I'll see how I can actually do it. But nevertheless, let's move on to rotational kinetic energy. If you can't hear me, just tell me. If I'm moving too fast, just let me know. Right, so in topic 5, if you recall, we talked about kinetic energy of a particle moving through space, and it was given in equation half mv squared. I hope you guys can recall that, right? But obviously, we've been talking about rotation for the last two or so weeks, and obviously, just like your kinetic energy, or rather the linear kinetic energy, we also have a rotational counterpart, which is essentially um, the rotational kinetic energy. Okay, so how we actually get the equation. I should actually just solve it or quickly derive it for you on the slide. It's not going to take long, but it's on the subsequent slide. I'm just going to draw quickly. So just bear with me. I'm just writing on this one. So we have half mv squared, right? So we know that's the linear kinetic energy. So we can just score the subscript L, right, for linear. So moving on to the rotational thing, one thing we know that your linear velocity is equal to your linear velocity is equal to radius times omega. I'm sure we're all familiar with this. And then we essentially substitute this formula into that one, right? So you get half mass, and we're gonna have now here we're gonna have r omega. What's going on here? Just excuse me, what's happening here? R omega squared. Why is my thing slipping like this? Squared, all right? And what happens here, we square both terms. So we have half. It's quite strange what's happening here. We have half the mass. So messy. Let's try this again. Otherwise, I have to use my board. So it's half mass. We have r squared and omega squared. And if you can remember what mr squared is, that's going to be your rotational inertia, right? I'm not going to write it. This thing is behaving very funny. So mr squared is I, which is essentially over here. This is what I've done. So mr squared omega squared, and the kinetic energy of rotation is basically equal to half your mass moment of inertia or rotational inertia times omega squared, and the unit is also joules. Okay, and I'll explain how it all works. But is it clear to everyone on now? I just got that formula. Are we all content on the formula? So that's the formula of today. Okay, thank you for that. Thank you. So that's what's important there. Okay, so I'm going to explain to you how we're going to use the formula. All right, let me just get the next slide. Okay, so that's okay. So assuming we have a ball rolling down the slope, we apply the same principles of the conservation of energy, and we have to look at the initial condition or the initial context towards a final context. Okay, so we get the top and then we look at the bottom. Obviously, you're familiar with this. So in the case of us having a ball or a sphere rotating down a ramp over there, let's quickly analyze its energies. Oh, so they call the linear part translational. So I'm just making where subscript T exactly is linear. You can use either linear or T. So it's translational. The KER will be the rotational, and then PE is your potential energy. Okay, so just looking at the top, right? Assuming we're moving from a rest, looking at the initial condition, which energies do you think the so-called sphere has? Does it have translational, linear? Does it kinetic? Does it have kinetic rotational, or does and or gravitational potential? Which of those three does the sphere have? Does it have 2, 3, 4, 5? Does it have all of them? I'm asking a question here. I think three. Is it three energies or just three of what? So the ball's at rest, like I said. Or the sphere, rather. So at point A, or the initial point, right, is the ball only possesses potential energy, right? So what happens is now the ball will move down the ramp or slope, and at the bottom here it will possess no potential energy. Obviously, we're assuming that this is going to be zero at the bottom, but then it will possess your linear part and your rotational part. I hope that's clear to everyone, right? And obviously do an example of that. Oh, what's going on here? Okay. So this also applies to your work theorem, your kinetic, your work energy theorem, where you essentially equate all the change in energies, which will be the work done. Obviously, the work done can be further expanded onto the friction. Okay, so what you're going to do with this is essentially the same as before, but the only difference is now we include a the kinetic energy of rotation, right? And remember, it only exists when the body's in motion, and it only exists if the body's rotating. So I hope that's clear to everyone, right? So when the body's moving down, particularly if it's rolling, it will possess kinetic energy. So this is the same approach we used in the previous one, but what's important is number 5 over there, where you typically have to convert between your linear velocity to your angular velocity, and obviously where the radius is the main variable between the two. So without further ado, I'll essentially explain with an example so that you obviously can imagine it better now. And obviously you guys will practice accordingly. Okay, so let me just open up one. It's exactly like the energy stuff, but all we have to do now is include the rotational kinetic energy. Is that clear, students? I hope you guys get me. Thank you, Africa. It's really nothing too crazy. All right, so we're on page 247, and we're looking at example 8.50. So I'm just going to paste it and then give you guys 2 minutes to just get maybe if you want to get the note up. And you'll see what I mean and how simple it is. It can be a bit tricky, but it's essentially all straightforward. So I'm just pasting up the question and then I'll give you guys 2 minutes. Okay. Right, so here we go. Page 247, like I said. Where are you? Okay, there it is. Are we all ready? All right, fantastic. Thanks, Cabello and Penny. So here we have a problem, and they say the goal is combine gravitational, translational, or linear and rotational energy. So we have a uniform solid ball. Obviously, solid ball is linked into sphere, right? Of a mass m and a radius r, and from rest at a height of 2 meters, it rolls down a slope of 30 degrees. They're asking you what is the linear speed of the ball. Assume the ball doesn't slip. Okay, that is very important, but it's okay for now. So what you guys can know. Okay, so let's see And now we're going to tackle this guy. So again, what we do, we look at the energy, the initial, and then you must equate that to the final condition. All right. So on top, it's from rest. So therefore, we have to, let's write all our energies. That's our translational or linear. This will be our rotational. Once again, that's exactly the same. Instead of mass, rotational, or mass moment of inertia, instead of linear speed, angular speed, we have a gravitational, and we do the same over here. Right? You know, I always start the question like this, and I engage with you guys to identify what is there. Okay. And for potential or gravitational potential energy reference, we assume that this is going to be, that level is 0, right? Obviously, that's an important thing to our reference point. Okay, Cabello asking you, so that you responded, does a body possess the linear kinetic energy or translational? Yes or no? On the top, it starts there, rolls down. So Cabello says does it possess linear kinetic energy? I'm saying yes. You guys agree with that? So I don't agree with that. No. Who else agrees with Penny? No. Okay. No. Yes, it doesn't. It's not moving. Right? Exactly. Does it possess rotational kinetic energy? Is the ball rotating? Yes or no? Exactly. Thank you, Mfunen Zizonke. Fantastic. Does it possess gravitational potential energy? Yes or no? Fantastic. Yes. Cool. So let's look at the final condition or the next part of it. Does it possess linear kinetic energy over here? Right? Is the ball still moving at this particular part? Yes or no? Yes. Thank you. Okay. Yes. Right. It didn't come to a rest yet. Is it rotating? Yes or no? Thank you for challenging Singalaka. Yes, it's rotating. Fantastic, guys. And obviously, potential energy, there's none because it's at 0. Do you guys agree with my formula now? Yeah. If you do, welcome. That means you belong here. So can you see all we have done is just include an additional what do we call this? Energy, right? It's particularly important for any object which is rotating. Okay. So once that is done, so always remember, we always look at the initial thing, what energy does the system possess, and what is the energy of the system possess in the second condition. Obviously, we're calling the initial and final, but there could be several, like from A to B, from B to C, from C to D. Just want to make that clear to everyone. All right. So we are looking for the linear speed. So we want to know V, right? Obviously, we find V, we can find omega, but obviously we don't have an R here. So obviously this is a bit of a mathematical type problem. All right. So let's quickly see. So we have MGH. We don't know the mass. We don't know the G and H. Obviously, you know, I don't like to give such problems. I typically give all the values, but just bear with me in this case. Yeah. So in this case, also have half mv squared. Obviously, we can already see we can divide mass out here. It's quite common through all of them. All right, plus half. So if you look at the previous page, this is a solid ball. Solid's ball, we can model it as a sphere, and if you recall, the formula for a solid ball will be 2/5 times m/r squared. Do you guys agree with me? Just look at that. Just let me know for sphere. That's what it should look like. Let me know if you agree. You guys agree? Before I move on. Thank you. All right, so what we do now, we substitute this guy into here. Like I said to you, I typically give you the mesh and radius. This is just an example. So just to give you an illustration of, of what's happening. And that's all we have on that side, right? So I don't need that. So we've done this, we've done this, we've done this, we've done this. All right, so the first thing we can do is divide out by mass. I don't know if you guys agree with me, because mass is a common variable. Then we have GH, then we have a half, and we have half squared, plus this will be, I believe, 2/10, right? And this will be r squared. Okay, I hope you all can see that. If I'm moving too fast, just let me know. All right, I think we did the right thing there. What we then do now, I'm missing something here. This is omega squared, sorry. Yeah, so that's omega squared. Sorry, I forgot about that. That's over here. Yeah. Okay. Are we content with that? Can you all see that? You're all happy with what I've done so far? If not, let me know. I'll give a moment for questions. Yes, Pushe. Anyone else? Everyone happy before I move on? That depending you're wanting me there, eh? You're multiplying this and this, guys, are half times 2/5 will give me 2/10 or 1/5. Are we all happy? Just let me know. Okay, cool. So what we then do now, obviously we know V equals R times omega, and that's embedded in here. So we say GH. Like I said to you, I don't typically give these math type examples, but the question is structured like this. So we can call it 1/5, just to make it easy for us. And over here, we have V squared, right? We can say R omega squared, which is essentially the same as that there, right? Hope you guys can see that mathematically. Hope you guys can see that. What you then can do is take out v squared as a common factor, and we have a half plus 1 over 5. We've got g, we've got h, and you need to solve for v squared. Just looking at the simple math, 2 times 10 times 5, 5 plus 2. I'm just using your lowest common denominator. So you have 5 over 2 over 10, and therefore we can solve for v squared. So can you guys find v for me? You guys are good at the math, not me. Let me know if you got it. 5.29, yep. 5.9, 5.3, exactly. Okay. Cool. So what I want to show you now, since we have this value, okay, that's fine. Was it clear to everyone? On how we conducted this. Now, obviously, we'll give you a question to do now. Just notice something. We're all content. Okay, so there's some nice problems. Okay, so I'm pulling up a problem from the textbook. Just give me a second. But go to number 53 on page 261. Let's attempt that one. Number 53, page 53, page 261. We can call that our exercise, or your exercise today. I'll give you guys around 5 minutes to do it. I'll place it up now. So if you're good with energy conservation, it will be exactly the same. There is essentially no difference between the two stuff. And this is it is important metric to note, especially when you're dealing with braking systems, clutches. I'm thinking of something, and also when you're looking at your energy diagrams within an engine. That is something important to know. Because I'm just going to paste the question for you, and then you can solve it. And tomorrow we're starting on topic 9. And once you've done topic 9, we've done basically 90% of the syllabus, not 95. Okay, I said number 53, right? Right place. Okay. So the visualization is exactly the same. There's no difference. I'll just paste it over here. So we still have a ball going down a ramp. And yeah, so what they want here, you have a disk in this case, got a mass, got 15 degrees, you've got the radius. This is something how typically, like what I mentioned, and we need the speed when it reaches the bottom of the ramp, and also the angular speed at the bottom of the ramp. Okay, what I also want you to do is determine, so at C, determine the energy, total energy, um, the total energy at the top and bottom. Ensure you show the type of energy. So what I'm essentially asking you is compute all the individual energies of the, with this potential kinetic, rotational kinetic, linear. Obviously, total energy will remain the same, but the purpose is to show you how the energy kind of transfers as it moves along the thing. I hope that's clear. Okay, so can I give you guys 5 minutes for this one? And then, yeah, all the best. Students, is the objective clear? Perfect. Practice. Yeah, are we winning? So 3.9 meters per second. I'm just looking at what's going on with the solution here. Okay, doesn't look remotely the same as what we're doing here. I think I made a mistake. Definitely. Okay, yeah. You guys agree with that answer? You guys agree with those answers? Bushe, Penny, Afrika? Okay, so I'm going to quickly run through it. I've seen that someone has done it and she's going to solve C in the meantime. So at the top of the rank, once again, we have potential energy, and at the bottom, we have our translational energy plus our rotational kinetic energy. First thing I'll do is work at my I, and the I for a solid disk, I believe, is a half mr squared. Hope you guys agree with me. So that's half times 55 times 0.25 squared. Can someone just give me that value? I can't put it was here somewhere. Okay. You should get 1.72 kilogram meter squared. So over here we have 55 times 9.81. And we need to find the height, right? Is this correct? So we know this is 15 degrees. We know the length is 4.5. Okay, so therefore we need to find that. And that looks like a cos theta, cos 15. So yeah, looks like sine to me. Sine 15 degrees equals x divided by 4.5. And we get x is equal to 1.165. Students, before I commence, do we all agree with these things? Who managed to get that? Are we in agreement? Is there any questions before I move on? Any questions, guys? Are we all happy with this too? Mfundo says yes. Let's see. Ms. Berkus, Bonani, Afrika, Akani, Mr. Sita, Cabello, Nelusi. Okay, that's good, guys. So put times 1.165. That's equal to a half. What's the mass there again? 55. I believe we're looking for v squared plus half. That's times 1.72 times omega squared. In this case, you have v over r squared, right? So to sort this out, obviously this is going to be v over r squared. R is 0.25. And if I square that, I should get divided by 0.0625. Close bracket. Let me write it up in meter. Okay, so this is the same. That comes down here. And your only unknown would be v squared over there. I'm not sure exactly what answer you get. Do we all follow the same approach here? You guys need more time. It is all clear to everyone? Mr. Nunu, Siamonga, Wendy, Zandile, Tabo. Penny says yes. Thank you. Okay, so assuming the answer is correct, right? We get the answer of what's that answer there? 3.9 meters per second. To convert for omega, it's 3.9 divided by the 0.25. And we show you the answer of 15.6 radians per second, right? What did you get there? Yeah, 50.57. That's perfectly fine. Okay, so you should get that. I think I fixed my calculator to a certain amount of decimals. Okay, so what I wanted him to do was compute the gravitational potential energy at the beginning. So this will be mgh, and this will be equal to 55 times 9.81 times 1.165. Okay. And you should get, just bear with me quickly. Can someone just maybe find the answer? I keep on using 9.91, it's fine. So you get around 628 joules, right? So what we're looking at is how this is split into both the translational or linear and the rotational. So working out my KEL, which is the linear part, and KER. Obviously, you know what it is. So what I'm trying to show you guys is how the potential energy essentially transfers to these two particular things over here, right? So half times 55 times 3.9 squared. So most of it is linear already. 275 joules, 418.2.75 joules. And then for our kinetic counterpart, which will be 1.72 times omega squared, which is 15.6, you get around 209.29 joules. So obviously, we add them up, you should get roughly the same. But can we see that linear energy, kinetic linear energy, is more predominant than the rotational one? So that's why he probably taught this one before that one. So it just shows you that at the end of the day, most energy is being transferred into the kinetic part. They're clear to everyone. Okay, great stuff. Guys, are there any questions before I move on? Any questions before I move on? Are we all good? So I want to make you aware that these questions, the kinetic energy question, is typically like a sub question within the what is this? Within the the kinetic thing. It's like, I mean, it's asked, but it's not like asked a lot, if it makes any sense. It's like more like a sub question rather than like a main type question. But there's obviously some slight variations. They can ask it. So what I thought, I'll give you one more, and then I'll do another type of question, and how you can actually use kinetic energy to solve problems. Okay, so let me give you one more as practice. So I found some nice ones in the book, so I'll just stick to those. Okay. All right, so this is incorporating the previous chapter as well, so I want you to be smart and figure this out. And after this, we'll do one more example, then we're done for the day. Okay, so this is again incorporating the previous chapter. So again, long story short, what I want here is the system's kinetic energy. And you need to obviously first find your mass moment of inertia, I, right? Again, there's two particles, which is easy. The first part is not considering the rod, and the second part is considering the rod, all right? And basically, the objective is find the kinetic energy, but obviously we know it's half I omega squared, and we need to find this guy. So obviously, you guys, I have some experience in doing this. So yeah, I'll give you guys 10 minutes for this. I'll roughly go through it, and then we can do the last example, and then you guys we're basically done with this type of the section. All right, is it clear? So I'll write the answers for you here as well, so you can see. Guys, is the objective clear? Make sure you're practicing. Okay, so that's the answers. Guys, is it all clear? All right, guys, are you winning? So can I get I of pot A? What's my I of A? Afrika, could you please provide it for us? Mfundo, what is I? Penny, what is the first I? 1.75. Let me see. 4 times 0.5 squared. I'm not going to work it out. You guys should be smart. It's definitely 1.75. It is correct. It's 1.75, 100%. That's correct, Miss Charlie. Nope, it's 1.75. Perfect. Okay. And once you have that, it's a simple plug and play of times 1.75 times 2.5 squared. And you should get 5.46875 joules. I'm just being very, I'm just exaggerating. Wow, I'm being descriptive for that value, but it's 5.46. So what's my I for the second part? Someone please tell me. So in this case, we're including the rod now, but remember the rod, so at least we have the 1.75, which is there already, but now I have to include the rod within our calculation. And yeah, we need to include the rod. But the rod is spinning about the center, so therefore we need to use the formula. Right, so I'm waiting for B's moment of inertia, or mass moment of inertia. So what's my mass moment for the second condition? $1.92. You guys agree? Fantastic. Therefore, the kinetic, how much is the kinetic energy? I'm just going to check quickly here. Half times 1.92 times, what's omega again? 2.5 squared. Yeah, I should get exactly 6. That's correct. I is 1.92. Right, you guys can sort that out. It's clear to everyone. Can we all tackle this? Okay. How do we get to, that's fine. So we need to use, we have to consider the rod now. So I'm going to call it I rod. And a rod's mass moment of inertia about its center is 1/12 ml squared. And you should get the balance. Well, it's a difference between these two values, which I believe is around 1.92 minus 1.75. Is that clear, Ms. Charlie? Okay. Cool. Guys, is there any questions with this particular type of problems? Any questions? So this is kinetic energy. That's the kinetic energy way. Guys, are we all on the same path here? Can we move on? Any questions, guys? Any questions? Please ask, because we have 4 weeks left. It says 3.5 weeks left. So now I want to see if this is possible before I actually. Okay. Cool. Yes, sir. Okay. Guys, any questions? So that's basically the type of, well, that's a concept. There is one more thing I want to do. Yeah, and that's basically all. But I'll leave it a bit open so we can conclude it tomorrow. Okay. So it's a similar problem to the one we did, example 8.14. I'm just gonna copy it and then we'll continue tomorrow on it. I'll briefly go over it like always, and then obviously start on fluids, which is the main thing. Okay. Remind me tomorrow just to give you an overview of the test as well. Yeah, that's obviously important. Okay, so this next question is, we're using conservation of energy techniques, right, to solve this. Obviously, we solved a similar problem to this where we had a bucket in Stellenbosch, Africa. But now we're going to try and do it a different way. So this is 58. And I want to see if we're able to actually do this one. Okay. So the question is, use the conservation of energy to determine the angular speed of the spool, shown in that figure. After 3 kilogram bucket has fallen 4 meters starting from rest. The light string attached to bucket does not slip, basically, as it unwinds. Essentially, there's no friction happening. Okay. So obviously, we tackle this problem traditionally is looking at the forces up, going with the forces down, right? But what I want you to think of it now is of this problem in terms of energy, right? So initially, our bucket is at the top here, right? Let's say over there. That's at the first condition. Why are you doing this now? Eventually, it drops down. I'm not sure my pen is. It's lagging a bit. Just bear with me, please. I'm going to close a few things here. That's the reason why it's doing this. Okay, right. So for us to calculate this, let's assume at condition A, or situation A, the potential energy is 0, and eventually we drop down from 0 to around 4 meters. Okay. Obviously, it has potential energy when it's higher. Or alternatively, let's do it like this, do it in reverse. Well, let's assume it's 0 over here at the bottom, and then obviously over here, the top is going to be 4 meters. I hope you all understand what I did over here, right? So you can work it either way, just depending where your reference is. So I'm assuming we have 4 meters on top, and eventually drop down to 0 at the bottom. So doing the energy type questions, we obviously look at the energy at A, or initial, the energy at B. So initial or final, A and B, same thing. So initial, we have potential energy. Well, that's at rest, right? You guys agree with me? Potential energy of this bucket. So you guys agree? Cool. And so at B, as a bucket is falling, or is it moving down, our bucket will move with linear kinetic energy, and the spool where the rope is on, it will be turning as well, and it will possess rotational kinetic energy, right? So that's why they give us the mass and its respective radius, right? So what we're going to have to do is obviously calculate omega, right? Obviously omega is related to R. So do you guys agree with this particular setup? Are we all content with this? Does it all make sense? So in the first state, the energies of the bucket, and that's essentially being transferred to the motion of the bucket moving down and the spool rotating. Is this clear to everyone? You agree with the analysis? So I'll park it here, and then tomorrow morning we'll quickly tackle this problem. I believe the answer is in the region of, let me quickly see, around 11, 10, 11, somewhere there. Let's see if we can get it. And then once you do this, you can try to do the example in the textbook of this kind of stuff. But I'm just showing you, this is how you're going to conduct these problems. And you can apply even linear stuff to this, but this is what essentially want to do. So I'll leave this here. I know it is a bit of a mouthful, we can just touch on this tomorrow and then embark on fluids. And then, yeah, okay. I'm gonna just check my email for something. That practice test was created by the tutors, and I'll post on Blackboard shortly. But just know that the practice test is not similar to the test at all. But it does incorporate good examples, nevertheless. But anyway, guys, thank you very much. I'll see you tomorrow morning on campus at 9. Okay, cheers. Please make sure you do the homework so we can discuss nicely. Thank you.